Okay, we're going to look at another example problem here involving projectile motion. This is example 3.6 from the book. We have a football that is going to be kicked off. It's going to leave the ground at an angle of 37 degrees and a velocity, that's like a diagonal velocity, of 20.0 meters per second. We want to know how high the ball is going to get, what is its height, how long is it going to be in the air until it hits the ground, and how far away will it be when it hits the ground. So we're going to assume that the ball leaves the foot at ground level, so the initial y position is going to be 0, and we're going to ignore air resistance and rotation of the ball. So we need to write down what we know, what was given to us in the problem statement, and that is that the initial theta angle here is 37 degrees. That's the angle that the initial trajectory makes with the horizontal. The initial velocity is 20 meters per second. So that is not the vertical or horizontal velocity, but the resultant of those two components, the diagonal velocity, if you will. Initial x position is 0, so we're setting up our x and y axes so that the ball is starting at the origin. So initial x position, 0. Final x position, well, that's one of the things we want to find out. Initial y position, why not, equals 0. How high up in the air does it get? What is its highest point? That's also something we want to know. Okay, so we've written our knowns and we've drawn a diagram. First thing we need to do is, when dealing with projectile motion problems, we need to separate the vertical and horizontal. So since we are given this initial velocity in a resultant format, we need to break that down into x and y components so that we can keep them separated. So here I have created another diagram, a little more close up here, showing the initial velocity of 20 meters per second and how we would break that down into x and y components. So I have highlighted here in red when we know or are using the theta with respect to the horizontal, that's a key part here, then the horizontal component is found by multiplying by cosine of the angle, and the vertical y component is found multiplying by sine. So we have the initial velocity multiplied by cosine of 37. That gives us 16. So that's the initial x component of the velocity. And we have 20 meters per second times sine of 37. That's going to give us the vertical component of that velocity. So now that we know the x velocity and the y velocity, now we can deal with them separately. So we're looking here at our y formulas for projectile motion in order to find the maximum height. And again, I've highlighted the things that we know. So in this first equation, we know everything but time. So we could solve for time. But do we, are we trying to find time right now at least? I should say it's not that we're not interested in time, it's just that we're not interested in it right now. We're trying to find maximum height. This one, y, the y position is going to be our maximum height, but we also don't know time. So here we have two unknowns. We have time and y are both unknown, so that's not really going to help us out. This last equation here, though, the only thing that's unknown is y, the final y position, and that happens to be what we're trying to solve. So that's the one we should go with. That's the one we should use. So we're going to use this equation, and we want to solve it for y. Okay, so I'm going to do that by subtracting this term from both sides. I'll take that over here. And so I'll end up with, I'm going to write it over here, the y velocity squared minus the vy naught squared equals negative 2g y minus y naught. Okay, now I want to get rid of the negative 2g, so I'll divide both sides of the equation by that. And I'll have vy squared minus vy naught squared divided by negative 2g equals y minus y naught. And then y will be equal to vy squared minus vy naught squared over negative 2g plus y naught. And that's exactly what I have right here. Now we can plug in what we know. We know that the final y velocity, when the ball reaches the peak of its trajectory, the y velocity will be 0 because it's reached its highest point for a split second. It's not moving up or down, and then it starts to come back down. So that's 0. The initial y velocity we determined was 12. That's how much vertical velocity it has to begin with, 12 meters per second. Minus 2 times gravity is 9.8. And the initial y position, we are saying that the level ground is has a height of 0. So it started at 0. So that becomes 0 right there. So we plug that into our calculator, and we should find that the height, the highest point of this ball's trajectory is 7.35 meters. Now we want to know how long it's in the air. How long does it take to go up and come back down? So we've got this equation right here that has time in it, and time is the only unknown. So I'm looking at my notes in the PowerPoint here, and I see, and I'm sure this was just copied from the textbook, that the textbook author uses this equation right here. But as I'm going through this presentation, I'm wondering to myself, well, why couldn't we just use this one? This one seems simpler. It just has t instead of t and t squared. So I'm going to kind of go off script here and give this a try. Let's see what happens. So the final velocity, when the ball gets kicked off and comes back down, the vertical velocity coming down is going to be the same velocity it had when it was going up, except it'll be in the other opposite direction. So it was 12.0 meters per second initially up. So when it comes back down, it'll also be 12.0 meters per second. It's just going to be negative. So this is the Vy naught, and this is just Vy. So Vy, that's negative 12.0 equals 12.0 initial minus 9.80 t. So if I subtract 12 from both sides, that's negative 24.0 equals negative 9.80 t. and then divide both sides by negative 9.8, and I would get t is equal to negative 24 divided by negative 9.80. That should be 24.0. And that is equal to 2.45 seconds. So let's compare that solution with what is in the PowerPoint using this other equation. Plug everything into that and solve it. 2.45 seconds. So we get the same solution with a little less algebra. This is a little bit simpler equation. And I think the reason why the textbook author didn't use it is because to use this equation, we have to take the logical leap of faith, if you will, that the final velocity as it comes back down is equal to the velocity when it went up. Okay, and that's not explicitly stated, but can be surmised. It can be intuited, and in our case, proven to be the case because we got the same exact answer. So 2.45 seconds is the amount of time the ball spends in the air. Here it goes through the air, 2.45. All right, and finally we want to know how far it goes. This is probably the most important thing a kicker wants to know when he kicks off the ball. How far is it going to go? So now we look in the x direction. We have these x formulas. This first formula isn't really very helpful. This is just essentially a reminder that the horizontal velocity doesn't change. The initial velocity is equal to the final velocity. So almost by necessity, we need to use this second equation right here, x equals x naught plus bx naught t. So the initial x position we'll call 0. The velocity, we found that in an earlier slide when we broke it down into x and y components. That was 16.0 meters per second. And we just found time to be 2.45 seconds. So that's exactly what we have right here. X is 16 times 2.45, and that is 39.2 meters. And so the textbook then, after solving that problem, gives us this formula for range. So if we want to know the range of projectile, and this is if and only if the final y and the initial y are the same. So this image I pulled off the internet is probably not the best one, because in order for this to work, we need to assume that the ball actually starts down here on the ground. We need to neglect the height of the pitcher. So if the ball starts from down here, goes up and goes down, the range being the horizontal distance that the projectile travels can be calculated with this formula right here. We know the initial velocity squared times sine of 2 times the, put some parentheses in there, 2 times the initial angle, the angle with respect to the horizontal, divided by g. As a side note, if you're curious, the angle theta, which results in the maximum distance r, is 45 degrees. So if you're, say, golfing or trying to launch a projectile as far as it'll go, the optimal angle at which to launch it with respect to the horizontal is 45 degrees. So we just have, I think, about one more example problem to go, and that we'll have to wait for the next video.